All right, so we can also do this alpha halogenation under basic conditions. And so in this case, instead of reacting with an enol, we're going to react it with an enolate. So you have some kind of carbonyl that has alpha hydrogens. You add some sodium hydroxide and some Br2, and then you'll get alpha halogenation. And the mechanism of this is pretty much what you would predict, right? We have some kind of acidic proton. We have our hydroxide, which is the base. It's going to attack this base. Again, I'm going to draw the enol or the enolate form. This is now a pretty good nucleophile. This is going to kick down, and then this carbon is going to be nucleophilic and attack our Br. And then we'll get this alpha halogenation. The issue kind of with this reaction is this hydrogen now just got a bromine added to it, which means it's an electronegative element, which means that'll help stabilize any charge that ends up over here. And so now this proton is actually more acidic than it was before before we added the bromine. So as soon as you add one Br, you're not going to be able to stop it. It's going to react further, and it's going to brominate the whole way. So instead of just being able to add one Br, you're going to add as many as possible. And then once you have that many bromines, something further is going to happen. Right, so now we've got a CBr3 right there, and that carbon is surrounded with some very electronegative elements. And so it's now a good leaving group. And of course, we still have hydroxide in solution. So this hydroxide is a pretty good nucleophile. And then we can get some acyl substitution going on here, right? So we have this tetrahedral intermediate. This CBr3 can kick back down and then kick off this CBr3, forming a carboxylic acid, and then our CBr3 minus, which will then deprotonate our carboxylic acid. Right, to end up with this final product. And then you would do an acidic workup if you wanted to form the carboxylic acid. So kind of useful is that you can create carboxylic acids from components, right? So for example, if you had this component right here and you added some sodium hydroxide and some Br2, you would end up with a carboxylic acid. Note that it's only methyl substituents, right? So this side has to be a methyl. So only methyl will do this. Because in order for it to be a good leaving group, it needs all three of those bromines on there. If it has some other carbon bond to it, then it's just going to replace any hydrogens that you do have with bromines. Right, so we'll just say others will just replace H with Br.